thank Chris for introduction for me, and I'm really excited to present on the COMET webinar. And at the same time, I'm nervous, as you probably know that I'm actually an engineer, and my expertise will be more like image processing and machine learning. So I have a good opportunity to work with Juliet and Fabian in the School of Earth Science, University of Bristol, and later on with the COMET people, which is really great. As a topic today, I'm going to talk about the how to apply machine learning to monitor the volcano deformation using InSAR data. First of all, I will kind of present a little bit of what the InSAR. I think most of you guys already know, but for some new guys, InSAR is the technique that uses the radar that transmit from satellite, and in order to calculate how the ground change, how it's deformed, how much of the ground movement. So basically, from the satellite, so they have the radar signal sent to the Earth and then get a reflect back and then record that signal. And when the same satellite come back at the same location and then send the radar signal again and receive it and then compare with the signal in the time one. And then that means if the ground movement, the phase of the signal between the day one and the day two, or the day T1 and T2 will be different. And in that case, we can calculate the phase with the wavelength, and then we can turn into how much the ground moved within that period of time. For more details about the InSAR techniques, I would recommend you to, if you want to know more about this, recommend you to go back to the COMET webinar. I think in January that Fabian presents about his work. He will explain very well how InSAR technique work. So what happened is what we use a satellite. That means we can monitor the ground change, particularly in the volcano case around the globes, particularly in the remote area where the ground-based systems are not available. As you can see from this world map here, we operate with the COMET LiCSAR system. They acquire lots of the InSAR image, which is called interferograms, around the world. And right now, we have more than 640 interferograms to process on. The good thing is that we can operate it automatically and monitor it a long time. However, it clearly cannot be processed manually. That's why we try to get the automatic system in order to monitor all this the data. The problems of this is when you are, the concept of measure the ground change is very simple, because you just compare the radar signal between 2 times. However, because the volcano is always in the kind of the area that have lots of the vegetation and have the water vapors. So what happened is, how do we know that the signal is actually the ground deformation or is atmosphere or noise? So this is for as example here. You can see this is the interferogram that I acquired from the Sentinel one. So the top row is the real deformation signal from the volcano unrest, and the bottom row here is the actually atmosphere. So we want to get the automatic system that can separate these 2 different signals. So this comes to the work that use machine learning. So I would like to go back a bit for the new student or some people that want to use the machine learning, what machine learning is. So machine learning is the way that you use the mathematical model that try to learn the patterns of the input and then link it to the output that you want. this also include the lots of application, for example, classification, that what we doing here, that want to know is it the interferogram is deforming or actually that interferograms is from the stable ground. And they also apply to other application, like you want to know regression, how to estimate the thing that change the prediction, and also some other stuff that you see here. The basic process of the training for this machine learning is you have the data that you correct. And then what we use here, we use the thing called supervised learning workflow. For supervised, that means we have ground truth. We have the expert that label what is the training data represent. For example, in our case, we have the what we want to know is the ground deform or not. So we have the expert that label that the deformation interferogram as 1, for example, positive, and then the rest of the data which is not deformed as the negative. That's for labeling process. And then what we have to do is the feature vector, have to get feature vectors, and then train the model. And after we trained it, and then we test the model and repeat until we get the best model out of it. So what is the feature extraction? Why we need it? Because the computer or machine not actually knows as we've seen. So we have to interpret the information or data that we have into some number. As for example, here, I showed the apple. If you want to classify apple from the banana, so you have to change this apple into some kind of numbers. Like for example, red histogram compared to banana, which is we have the same, different histogram, and use that to feed into the computer. And then the computer or machine to build the boundary, which is called hyperplane, which is the different model method that you can have, and divide the feature that we extract, try to separate them as far as possible. So then when the new data come and they convert to vectors and a feature, and those features will be lie on the feature space that you will know that actually the output should be what it should be. So in conclusion for the machine learning, so you have input and you have feature extraction, and then you try to classify to get the output. But for the last, I think about like 5 years, the computer is a lot faster. You have better memory, you have better storage. So the method that actually being proposed like more than 20 years ago called neural net become more popular. So what we call it called deep learning. So the process is merged between the feature extraction and classification into one network. So what network is doing is get the data and learn this data and try to adapt itself to get the feature that match better for the input. And because we're working on the image, which is interferogram that you've seen before, so we use the method called the convolutional neural network, or CNN. So as its name, the convolution, it uses the convolution operator. You see another animation here. So actually it's like a filter. So what happened here that you define the size of the filter, for example, here is 3 by 3, and then go through all the image or feature maps for each layers and then get the output. So CNN will have lots of several of the convolution layers. So each layer output we give at the feature maps. It worked really well for the image input. Why is that? Because it's surprisingly, it works as our visual systems. So each convolution layer will extract feature from the really low level features, which is like line, blob, and dot, and then get the feature maps and then feed into the next layers. We need to get to for example, connect those lines we will learn to connect to be corners. And then for the higher layer, and those corners we connect to triangle, for example, so we get more complex shapes. And after many layers, you will learn the semantic meanings in that image. For example, you have like triangle and square, and then it become house, or lots of the curve then become flowers. And then all of these will connect into the, they call fully connected to get the features for represent to that image, and use softmax to convert it into the probability. So this is the framework that we propose. So we have the training process, which is the same as the machining that we talked before, and then model with CNN. After we get the model that we put, and then we use that for predicting for the new coming interferogram to get the output. So then I will get through all of the process from here. So first start with the data. Further, I have to say, because when we use the deep learning, which is the network learn the features from the data, which is we call data-driven method. That means we mostly spend lots of time to try to prepare good data. So then the model can be learned from data straight away and can have a good representation of the characteristic of the output that we want to find out. For this volcano monitoring test, you're probably not surprised that very difficult, as in the positive or the deformation actually not avoidable very much at all, compared to the negative sample, which is like background or sample or stable ground. So we will come up with solution for the imbalanced data set. So when we start in first back about 2018, we use the NVSAT data set, and because that the data from Sentinel 1 is not yet available very much. So from there, this is a very traditional method how you increase the number of the majority class, which is now positive. So we have only 300 positive samples, and we use the data augmentations to increase the data. How do you do that? You can use the rotation, flip, distortion, or sometimes put some noise in, and at that works, so you can include in 10,000 positive samples. And also because we have lots of the negative samples, which is like background and noise. So what we're doing, we have to downsample that by randomly selected the patches that contain edge. So basically, if those interferogram doesn't have any edge in there, which is what we want to take it these fringes here, because it's deformation. If you don't have any edge, meaning it's homogeneous area, it's definitely not the signal that we want to find. Another method that we used, so you can see from the previous example that because we have so limited numbers of positive volcano that deform, and if we want to use that model for the whole detect for the whole global, the whole world, it means that we don't have enough characteristic of deform. But luckily for the geoscience here, so all the deformation under the ground already been studied. So we decided we use the synthetic data sets to increase the set and also to give more generalization of the model, because now you can see that we include all kind of the possible of the fringes that could happen, and then include with the stratified atmosphere, which is get it from the weather model from the GAR course, and then add into the turbulent atmosphere. So this is the final interferogram that we use for training. So this is the for the positive sample. For the negative, it will be S plus T only. So deformation is 0. So now we have the data that prepared, And next, talk about how to get the model. So we use the CNN because we want to only detect those fringes, and we use a technique called transfer learning strategy. So we use the pre-trained network. There are so many pre-trained networks. So what the pre-trained network means, the network that other people they already introduced by training with the natural images, like hundreds of thousands images, with the for this case, for example, like 1,000 classes, 1,000 objects. So make this object to learn almost objects in the world, like cat, dog, house, and everything. So these layers, we already learned and have the filter or kernel that have the weight that already suitable for natural image. So what we're doing here, so we have this training, the weight is already there. So we remove the last few layers and then replace it with a kind of new completely network, initial with random samples. And the output will be only two classes, which is deformed or undeformed. You can see, for example, here that they have many structures that being proposed, and generally, when you for the object classifications, deeper networks seem to give better performance because these objects have the more nonlinearity. However, that's not the case for our work because we want to detect fringes in the interferogram, which it have the really strong feature of edge round and round, and that not actually that if you compare to we want to classify for 1,000 objects. So when we tested, we found that the AlexNet, which is one of the earliest network, had performed the best. So it's shallower because our applications don't need to have the nonlinearity as much as for the object classification. So we stick with the AlexNet. And now we train, and then I'm going to talk about the prediction process. We tested with the Sentinel one InSAR data. I'm showing you here as the grayscale images because most of you guys, when you look at the InSAR data, you can see it's like a colorful that represents the phase change between -pi to pi. But it actually, for the network, they've seen these inputs at only one channel, which is the grayscale as the image. So that's why I'm showing you here that we actually use the grayscale images that normalize from 0 to 1. And these have been cropped around the volcano with the resolution of about the 0.5 in latitude longitude, and each patches have the 500 to 500 pixels. Now, what happened? We got the model and we have the new data here. Because first of all, we need the patch that have the same size of the input of AlexNet, which is 224 by 224. So what we doing here is we first we apply the edge detection because of course the homogeneous area definitely to be the background. It's not going to be a deformed signal. And then we divide this interferogram into overlapping patches, and each overlapping patch here will be fit into the model to learn and not to learn, sorry, to give the output as the probability of being deformed. So after you get the probability of each patches, so then we merge those patches together using the Gaussian merge. So you can see that finally we got the probability map. The dark one means that the probability is very low, and the brighter mean probably very high. So in this way, we can use the local maximum method to detect where is the ground deformed in those interferogram, that 500 by 500. I have to say that because the deformation signal is not always happen at the center of the volcano. That's why we need to apply this method to see where actually the ground is deformed. So this is an example of the interferogram that we found. The yellow is tell you is the probability. The brighter mean the higher probability, and the controls are saying that it's the probability more than 0.5 and 0.8. Generally, for any object classification, we always put the threshold of half of the probability. So more than 5, it means we found the positive samples there. So with the first trial, we have the 20,000 interferograms from Sentinel-1 data sets, and training by synthetic alone. So we found a positive about 334, and with the 41 true positive and quite a lot of the false positive there. So what happened is what we get the expert to check, which is Fabian, and then we feed this all the positive back and train with the first data set here, and then remodeled it. And you can see that after the retrain with some of the false examples, so we now, when we go through all this, manage to down the false positive down to 9. So I would like to mention a bit that these systems that have been deployed, and then you can check the result of the volcano around the world on the COMET portal under this website here. Okay. I'm showing you here. This is now we test with the whole the world that we have. The latest time that I test is like 15th of February. We have more than 640 interferograms and more than 1,000 volcanoes around the world. And we detect about nearly 4,000 interferograms that are positive. So we plot it on the world map here. You can, and this is also have the histogram that I put here, that you can see that most of the volcano that being detected as the positive is from the Sierra Niagara, which is the really high big detection here. So based on the more than like about the 4,000 interferograms, 35 more than 35% is from Galapagos Island that you can see here, that moving. There's other that we detect a lot is also Fujisan here. This actually, what I understand it is because of they have quite a high atmosphere there. That's why they come to the how to improve this false positive, so we can apply atmospheric correction. We have tried using the dark course model to remove some of this atmosphere, and we found that it improved a lot. So if, for example, if this is the false positive before, and we've been detected when it's incorrect with the data, we have lots of fringes that look like it could be the shape of the volcano, and it look like a bit deformed. But after remove those atmosphere, so those fringes are gone. So then now the machine learning or CNN will not detect that as a positive anymore. However, if you have the good deformation, even though you remove those atmosphere, there's still some deform that you can see. So if the weather model available, so we can include that in the automated system, so then we can improve the detection accuracy. However, there's also some false negative. For example, in this result from the Sentinel graph, so you can see that in the middle one, which is show only one fringes here, it acquired only like 12 days. Didn't have many fringes, but didn't have enough features that CNN can detect. So what we want is actually the CNN detect really well if you can see a lot of fringes like this. So, but the problem is lots of volcanoes around the world doesn't have the fast rate enough that the show fringes in the single interferogram. Because one fringes, if you have like 12 days, the interferogram is have to be moving as like 85 centimeters per year, which is quite fast and rapid. Only if you have to create the interferogram that produce from the really from the long length, like a year or 2 years, for example. So we come up with the techniques that we call overlapping techniques. So what we're doing here is we apply gain to the phase. This is your example of the idea. This is the original signal. We can see you have only one fringe here. The CNN can detect about like 4 or 5 and 7 when the noise increase. So that means if, for example, there's a noise here, and if that volcano movement is less than 7, the CNN cannot be detected. So what we're doing here, even apply gain, so and then rewrap it again, so we can see more fringes in the interferograms. So you can see that now the threshold after the rewrapped it apply like at the gain of 2, 4, and 8, the threshold that be able to detect is moving to the smaller value. So it's moving from nearly 5 here, 5 centimeter into the about 2.5 that we can detect the change of the rate. However, you have to be careful because if we wrap it too much, it means they can create the other artifacts that can confuse the CNN, because we never learned about this before. So this is an example that we try at the camp in Italy. So we plot the accumulate time series, and we know that we have the uplift start about July 2017, and then we have the rate about 85 centimeters per year. So we apply, they have two points here, A at the reference stable ground, and B as the where it's deformed. So this is the result from the CNN we apply for each single frame of this. If we use gain to 1, that means that for the original number of fringes, so we have the blue probability here. The CNN detect the where is the ground change is about X months later. However, when we apply the some gain, so then the threshold is 0.5 here. Sorry, I forgot to say. That means when it could detect that something at the ground change are moved toward to the closer to the when the episode start. However, when we apply too much gain, which is like X here, for example, although it's say, okay, we detect the something change at the where the uplift start, but before that, there's also some false positive over there too. Therefore, we propose to average all of these 4 so that we have the kind of more robust and stable and reasonable results. So this is, you can see that now the no false positive before the event begins, but can detect the ground deform about 2 months later. And this is another example that we tested for other volcanoes around the world. So back to the first result that I forgot to say, that we plot the histogram, and we see that which volcano that we want to monitor. So then we apply the accumulated time series on those volcanoes, and apply the on-scene then to see if they can detect change on the time series or not. You can see, for example, here we have Domeo, Coverty, Tamura, and Moyle. These are very slow and sustained deform. So the for example of the Domeo here, so the change with the like 15 centimeter per year, and the Sentinel can detect about 5 months after we start the time series. And when for the Cobanti, so then this is the slower rate of the deform, and of course the Sentinel detected a lot later that something changed. This all happened. I also show you some example of the outer L as well. That when there's some intrusion happen, the Sentinel managed to detect that, and also when after they have some ground slowly deform, subsidized deform here, the Sentinel still give you the positive example. Another example here is the regions from in the Iceland. From this plot, you see that the center of the volcano is here, but where the ground change is on the west and the east. For the point one here, so we observe that they have the ground slowly sinking, and then suddenly they have a uplift here. So what happened here is the Sentinel managed to gradually detect it at some point. However, when the ground changed from the slowing go down to go up, the cumulative signal now back become 0, referring to the first time of the time series. So that's why the Sentinel is now dropped to give the drop property of to 0, and then start to pick it up again later. And this is another example of the slow deform. I think it's going down because of some kind of man-made power plant that they get the ground is sinking, and we monitor it using the Sentinel, and they showed some change detected about 2.5 years later. Okay, so another example that this is the recent work. So we applied those volcano method to another different of the signal to detect the ground deformation in the UK. The difference here is the signal that the signal sheet velocity here are acquired with different techniques than in the volcano. So you can see in the volcano case, the interferogram are dense, but for this signal, I understand that it's acquired with the persistent scattering. So then the signal that we got here is sparse, and the pixels are not connected. So in order to use with the Sentinel, as I mentioned before, the convolutional operator need to operate it as like a filter. So then you need to have the pixel that have value that connect to each other in order to filter it out. So when they touch sparse and spiky like this, what we have to do is come up with solution that use the spatial interpolation. So this basically like the prepared data set in order to make it suitable for CNN. we also apply the synthetic data set for this work too, because of course we don't actually have the ground truth to detect for a start. And then we also have the overlapping technique because it is a localized motion, so that we already presented already. Just show some example that what happened if the data set is sparse. This is the area that have the problem is subsidized because of the mining in the past. Or what we consider what we want to detect is around this area and that area. If we use the traditional method that just interpolate it because it is in the urban environment, which they have noise as well. What happened is the traditional interpolation that also present lots of the, it become increased the noise that appear on there compared to what we use to call metric completion. It's based on the statistic that assume that the Gaussian distribution, and we also apply the soft thresholding. So basically for this method that we use is interpolate and also denoise at the same time. So this is the velocity map. What in order to apply Sentinel, so we need to get it back to fringe. So it become look like wrapped it again. This is the example that we can show you. So if you can see that in our work, our interpolation method can see a lot better fringes. So this is like more suitable for seeing and to get these features compared to if you have the traditional method that you cannot really see the fringes because got interfered a lot by noise, and also here as well. So, so this is the result that show the probability that we detected where the ground is moving in the UK. So I come up with a conclusion. I think it's a bit short for this presentation, sorry. So we applied the deep learning to the draft InSAR image to detect the rapid ground deformation. And this can be used for monitor the volcanic activity. So we have the problem, the imbalance data sets, and so then we use the data augmentation and synthetic examples to improve the model. And we use pre-trained AlexNet to do this. And for monitoring the slow and slow deformation, we use the accumulate time series with the overlapped data. And we also apply this to the open sources with the spatial interpolation. I plotted here that the framework that can be, we think that we can use for automate the system. So we have the InSAR data from the LiCSAR. And we first applied each interferogram with the monitor, the global that we showed before. And if we found that the probability is high, so then we plot the time series to show how that perform as well. And if we have the data set from the with the model, so then we can apply the atmospheric correction to improve the data sets. For future work, what we thought that we should do is to apply anomaly detection or self-learning method, because now what we have is we use the label data, but it doesn't mean that it covers everything in the world. So we want to have another model, so in order to get better monitoring system. So use the anomaly detection that learn the global statistic of the normal events. And so then when the ground deforms, and that would be detected as the anomaly detection. Thank you. This is the list of applications that we have. So if you want to know more about it, so please visit it. And I'm happy to take any questions.
Thanks so much, Pui. That's really fascinating and cool stuff. I'll just start off with a question. So how can you use these methods to estimate like uncertainties on deformation and amounts of deformation and maybe like model parameters? I think you might have covered that, but.
Can you say again what you mean?
If you're trying to get a model of how much volcanic deformation there was, or some, like how much uplift or something like that, can you get at uncertainties on that?
Unfortunately, no.
Okay.
But because we just only like kind of detect it's deformed or not deformed, so it's like a binary classifiers. But we did have the probabilities. So normally, if you have more fringes, you get higher probability. So lower probability, lower fringes, lower number of fringes mean then will give you the lower probabilities. So that could be used right now with the it depends on the because interferogram created from 2 different times, right? So if the time is too short, that I showed you before, meaning that the if it's only 1 fringes, the thing then cannot be detected. That's why we come up with the technique they call overlapping, so that we create more fringes, and then that lower the threshold, because it used to be, say, detect have to be more than 18 centimeter centimeter per year, down to only like 5 centimeters per year, for example. Yeah, so basically we cannot say exactly what is how much the ground deformed from the scene in.
Okay, cool though. Cliff Thurber has asked, is any of your workflow available for others to use?
Well, I mean, yes, if you want me to share, of course. Yes, we discussing that if we should like put it on GitHub, for example, and then you can use and try out. Yeah.
Yeah, so Pui's homepage has a link to some code and some data sets at the bottom of the page that to get started. So,
yeah,
right. Cliff says, not for me, for other colleagues. So yeah, thanks for
yeah.
that's a good question. Matt Gaddis has asked, hi Pui, great talk. You have a very impressive set of training data. Do you think you're close to being able to train your own CNN from scratch?
Well, now because we use pre-trained network, if you really want to train it from scratch, it's possible, definitely. It just takes longer to train. That's why the pre-trained network we use, because it's already done. The weight is already detect the edges of the object. But if you train from scratch, that means, yes, basically to have the more iteration loops in order to get the good results.
Okay. So in the Q&A, Richard Serrano has asked, is anybody using, you or your colleagues using these kinds of methods on South American volcanoes in particular, or maybe has plans to?
To be honest, because I'm in engineering, but I know that there are lots of people in the earth science working on the South American volcanoes. Yes, I should think so. Although I do understand that they probably not yet use the machine learning, but they might use some other method on the South America volcanoes. But because this one did run around the world, so that means the volcano in the south of South America also have the result that show on that website as well. The website that I showed you before, the COMET portal for the volcano detection.
Right. Cliff Thurber's pointed out Laguna del Male, Chile was on the detection list.
Yeah.
Yeah, so Richard, so Pui's colleague Juliet and a lot of her students and some other people at Bristol study Central and South American volcanoes. So keep your eye out for that. Pablo Gonzalez has asked, thanks for your talk. Do you have any intuition of why retraining AlexNet 2012 performed better than newer and bigger models? Do you expect this to hold with other future models?
It's because but you probably think that the deeper on the network or newer or bigger network models that get better performance in terms of object recognition or object classification that have been published, but that for the objects that in the natural images. But from our case, this case particular is we want to detect fringes. So you can see that like a really round and round. So those are really kind of, you don't really need the higher features or semantic meanings of that. But what we want to lower level features. So basically, if you have the deeper network, what happens is to more confused and can be easily overfit as well. And because the LiCSAR is shallower, and that only extract the feature that enough, not more or not too much, enough for this case. That's why they get better results. Yeah.
Okay, cool.
So basically, this application have less nonlinearity than the other object detections.
Okay. Okay, so Cleanthus Karamvasis has asked, thanks for the excellent presentation. This interesting work. I have two questions. First question, is there any selection strategy between long and short temporal interferograms? Do you have any? How do you choose which ones?
For training?
Presumably.
We would like, what happened is, like I said before, because the CNN is data-driven method. So the performance of the network very highly depends on the data. So what we be doing is we try to get the training that cover the most cases that we want to take around the world. So the trainers that have to kind of vary from short and long. So we have the different number of fringes, different size of fringes, basically different characteristics that are the volcano, because lots of volcanoes around the world, they have the different characteristics. That's why our training there is like try to cover all of that, not bias to only one. That's the answer to make the model with more generalization.
Okay. And then
the answer.
Yeah, awesome. This is the second question. Do you have any best practice suggestions regarding how much to overwrap in order to sufficiently model subsidence phenomena?
This is really, you can see in the slide that I showed you before, that if the data is clean, so the you can see fringes easily. So more fringes, that's good, that's fine. No problem with that. So we didn't have that problem. The problem becomes when you have the noise interferes as well. So when you have more, you overlap more, you get the noise also more as well. So what happened is, when this really depends on the resolution of the image that you use, and at some point those fringes become too close, and that like aliasing effects. So CNN cannot see as the several lines together anymore, and that point CNN cannot detect it because they thought it's the noise. Yeah.
Okay. So Milan has asked, do you plan to use the same network or same methods to identify coseismic deformation from earthquakes?
Yeah. I only tried it for InSAR. I never tried the co-seismic signal. So I guess it's probably quite similar. They have lots of features as well.
Yeah, if it's a big enough earthquake.
Yeah, I'm sorry that I don't have much knowledge about it, but as long as I have features, so it definitely work. And oh yes, actually, we tried on a Tau volcano. Is that right?
Tall.
They have earthquake as well, and they have so many features. Yes, the method detected very well because it very clear features there.
Cool.
So it definitely work. Yes, it works.
Yeah, I guess you'd have to maybe work out something about the different quadrants of deformation of different directions. So cool. Kurt Sollander asked, how many interferograms were developed from Sentinel, I guess, in this work, and what kind of software did you use to do this processing?
The techniques that use, I'll say it again.
How many interferograms were developed from Sentinel, and what kind of software did you use to do this processing? I think I guess, what did you use for like getting the InSAR interferograms, or where are they from?
It's from LiCSAR system from COMET.
Yeah, so Kurt, so LiCSAR uses gamma as its main InSAR processing, and then SNAFU to unwrap. And then we have some options as far as atmospheric, like GACOS.
Thank you.
Yeah, no worries.
Because I assume that machine learning have the not the deep techniques about that. So.
No, that's fine. Same here. I'm just practicing saying that sentence that I just said. Milan is the one that knows how to do that stuff.
Yes, I said before that if you want to know more about, I did mention that. So Milan just have the presentation last month, isn't it? So you can go back to watch that.
For sure. All right. Jose Marmolejo has asked, my question is regard to data augmentation techniques. If the phenomena you wish to study is information tied to regional structural trends, such as stress fields or pre-existing faulting, does rotation and translation, or et cetera, have any effects that you could generalize?
Yes, definitely. That's why we also apply the synthetic data sets. I actually said before, because when we first start, we have only a few volcanoes actually deform, and that's definitely not enough to represent all volcanoes around the world. So that's why we use the synthetic data sets. Yeah.
Okay, thanks. Tawhid Nozad Khalil has asked, is it possible to detect different kind of deformation with different deformation rate? For example, coseismic and interseismic in the same process, or do they need different models and network designs?
I never seen the data, but as long as it has the same features as you can see in volcano case, it should be able to detect it. However, I would think if it's not the same, it have the slightly curve, for example, or different types. So retrain it. You can start it from this one and then retrain with your data set, and should work better.
Right. So I guess if deflation and inflation happened at massively different rates, it might require maybe different algorithms. But if they happen at similar rates, then you can just use the same.
Because right now, this method would train in a large the range, the good range of the rate too. So then the different number of fringes, and each, the gap between fringes could tell you the spatial resolution and how much it deforms. It's also we try to cover that as much as possible. So it should work, but again, if it have the different, more like spatial characteristic, because the volcano is more like round, right?
Yeah.
So it has different spatial characteristic that you probably need retraining.
Okay. James Dalziel has asked, hi Pui, thanks for the talk. In terms of detecting deformation in the UK, what kind of usable resolution can you get? For smallest subsidence features such as sinkholes, is there a certain size below which the CNN just regards it as noise?
Yeah, so sinkhole doesn't work because it's only 1 or 2 pixels, of course, because the CNN characterize the spatial resolution, spatial characteristic of the signal. So sinkhole doesn't work. So what my friend study is instead of using spatial resolution, so you have to have time series, because sinkhole would seem to have the some kind of slightly dropped on the surface and then before suddenly dropped. So they have to use a time series for doing that instead.
Okay.
Yeah. I think you call RNN, yeah, recurrent neural network.
Yeah, okay. So Roland Bergman says, thanks for the great talk, Pui. Have you considered, I think this is sort of what we were talking about with the previous question, which Roland asked us before we talked about that, but as far as tall volcano, resolving secondary faulting events associated with your volcano targets.
What does it mean in terms of?
Sort of what you're talking about with like tall volcano, with the earthquakes that happened around the caldera.
Yeah, so again, as long as it looks like fringes, it's detected.
Yeah, okay. Yeah. Right. Okay, so Pablo Gonzalez asks, in one of the figures of the Sierra Negra volcano, the false detection examples, I noticed that there was substantial smoothing. Perhaps I missed this, but how do you treat the low coherence areas? Do you mask them out or smooth them, or?
No, not at all. It just got in the low current, it would look like noise. And CNN, it seemed to be really good to dealing with noise, actually. So we just fed it as a noise. And if those fringes have some noise as well in there, CNN still be able to detect it. Yeah, because we saw it in the Sierra Negra, I think. There's sometimes we have the noise interfere, but we still, the CNN still detect the fringes.
Okay.
Yeah. Or otherwise, we treat it like a negative sample.
Right. Okay, so Agu has asked, thank you for the great presentation. There are other real world processes that could have behaviors such as geothermal or volcanic signatures. How do you, if you have overprinting from multiple different processes, is there a way to train the algorithm to distinguish between?
So you mean that the signal have multi-channels? Is that right?
How do you exclude other geothermal-like displacements? I guess if you have an area where there's, for example, like sinkholes and a volcano, or sinkholes and geothermal extraction, would that require you to just look at the results, or do you think these algorithms could distinguish types?
What we're using here is a classification. So for this particular one, the model that I'm using is not going to work, but there are the other work for the, it's called to separate the signals using other type of the convolutional neural network. For example, it's called deep image multiplier or double deep or something like that. So basically, you can train to learn how the signal combined, and then the output would be 2 separate signals. Okay. So basically, you have the different models to do that. Yeah.
Okay. And then last question for now, or maybe second to last. Sonny Sisilakar has asked, do you think this method can also be used to forecast volcanic eruptions?
Well, if what I understand it, if you monitor it and when the volcano arrests or deform, it's linked to volcano eruption. So what we can do is we only monitor how it deform, but we cannot just predict when it's going to erupt. But you have to just say that you have to be careful with that. What I understand that, for example, like definitely you cannot use CNN to detect earthquake because it just happened. It's happened, right?
Right.
So,
yeah, we have that problem.
Yeah. So we can just only monitor when it's deformed.
Yeah.
But that deform linked to eruption or not, I don't know. Yeah.
Yeah. Michelle Yip says, thank you for your great talk. Besides the limit on area of deformation, may I ask what is the detection limit for displacement rate using this method? If you have a target with 10 centimeters per year displacement rate, can that be identified?
Well, like again, because this method is like a binary classifier that say it's deformed or not deformed. So right now we only can say that when is the ground change about 5 centimeters per year, and above that, the CNN just say if there's something change. So we cannot use this model to do that, but that if we want to link that to the proper number of the rate, so we have to use this called regression model instead. So it won't train as the binary as the 1 or 0 anymore. So the neural network will be used to train to get the output as the number, like continuous number instead, like when people doing to predict like finance, for example. Yeah, so have to use the regression model, not the classification model to do that.
Okay. Okay, I think that's all the questions we have for now. So yeah, I think we can wrap things up there. If anybody else has questions for Pui, feel free to contact her by email, and we'll put the recording in this webinar up on the COMET Webinar's YouTube page in a couple of days, or a few days after editing it. And once again, we have our next COMET Plus webinar is going to be Endra Gunawan on the 28th of May. So stay tuned for that. We'll send some emails out about that. But for right now, if everybody wants to join me in thanking Pui for her fantastic talk and really interesting work. And I look forward to seeing where this goes. More and more.
Yeah, thank you for inviting me to the talk.